Yeah, so my talk today is titled Research Data Engineering with Apache Parquet. Just a quick introduction about myself. I'm Dave Bunten. I'm with the software engineering team here at CU Anschutz within the Department of Biomedical Informatics. For more information about the team and what we do, feel free to visit the web URL below. And I also mentioned that I'll be happy to share the slides after today's presentation. So don't feel like you have to scribble this down really rapidly. And I also wanted to start off with a big thank you for everybody who's attending. I really appreciate everybody being patient with me and listening to all the things that I have to say, acting like any of this makes any sense at any moment. Yeah, thanks, really appreciate it. So a quick presentation outline. Data challenges. We'll talk about the Apache Parquet format, and we'll talk a little bit about the future in terms of things that might be interesting and how to use the Parquet format. So a quick quote here, you will never find time for anything. If you want time, you must make it. So here in this case, we mean literally with the Apache Parquet format that we have to develop a way to be a little bit faster. We have to find time to make ourselves quicker. So data takes a ton of time to store and retrieve from files. Some questions to ask yourself in terms of why this might be important is what is the time cost of the file formats that you use today? Think about the file formats that you're using and how much time it might take to read those in or do various work with them. And are we prepared for the future of data needs? So how are we preparing both ourselves as well as others with the data that we're using? And then can we make time by using alternatives? So just sort of a rhetorical question there. And a quick theory here, this is just kind of a fun idea that I usually have in my head as I'm developing things. We need to act a bit like time travelers in order to be good stewards of research data engineering. So time traveling as in reducing time durations, time traveling as in avoiding the need to reduce time in the future, and time traveling as informing those in the future about what's already happened. So we'll cover these aspects through the Apache Parquet format, which can help us be good stewards of research by using less time and enhancing the key approaches with data that we take. First, we'll cover some brief examples about data challenges. So this is just a quick visual example of some simple tabular data. So we have three columns here, column A, column B, and column C. And we have two rows of data that are just really column A is integers 1 and 2. Column B is a string, a single character string, or maybe just a character, depending on the data that you're using, or the technology that you're using to read the data. And then column C is a floating point number. So an example of how this data might look within a CSV file might look something like this, where we have the columns outlined in the first line of the file, or the column names outlined in the first line of the file. And then we have the column values in the second line of the file, and then and also the third, and so on. Usually the comma indicates the separation between the values. And CSV has been around for a long time. It's really great on its own. And some of the advantages that it comes with are that it's simple. It's really easy to decipher. It's interoperable. Pretty much anything on the planet today can read a CSV with good assurance that it's going to operate pretty much the same way with few variations there. It's also human readable, meaning that we can open it up with a text editor and take a look at it just really, really quickly to determine what's happening, which is especially useful if we have any problems with the data. Things that might be going awry are really quick to diagnose because we can just open it up in a text editor or view it directly within the browser. But what about more challenging scenarios? So let's say that we try to hold the following data within a CSV. So notice that the column header here, or the column name, specification all of a sudden has some differences in terms of what we might see. All of a sudden there's a space in between col and B here, whereas the other columns have an underscore, and then all of a sudden this one's all caps. Why was this all caps? We may not know. There might not be any notes to determine why that is. Another challenge here is that we have an empty data value for that first column here. And also notice that there's only 3 values here. So we're missing the 4th value, which means that all of a sudden we need to infer what's happening in column D for this first row of data. Another thing that's happened is we have a string that represents a floating point number, which is going to be treated like a string inside of whatever software that we're using, and can immediately make the data that we're working with much, much larger than it needs to be, because strings take up more space in memory than, say, a floating point decimal. And then also we have this interesting null here, in contrast to, say, the null up here, which is just an empty value. How we're supposed to treat this might be something else that we have to infer. And also there's this interesting dictionary or struct that we have as column D's value here. So we have a nested value that we have to take care of that's sort of implied via these brackets, but CSV has no specification in terms of how this should be handled. So that's going to be entirely up to the data reader that we use in terms of how that's handled. So that's a lot of challenges for just like three lines of data inside of a CSV file. And I'm certain that all of us in the room have run into some of these problems before. And they're not necessarily things that anybody intends to inflict upon anybody. They're usually accidents. So just to kind of go over some of these challenges with CSVs, there's no data types that are listed with CSVs. It's not a requirement. Sometimes we'll see this inside of the column names prefixed with, say, the data type and then the column name. But this varies, again, from reader to reader. There's basically implied translation for every read that we do on CSVs. We have to determine what that data type is and then make that translation on the fly. And that happens differently depending on the programming language that we're using and the library that we're using to read the data. CSV data is expensive to slice in terms of calls and rows. This depends, again, on the technology that's being used, but by and large, CSV is row-oriented. We'll get into more of what else there is as far as how to organize the data here shortly. Missing data handling is, again, it varies from data reader to data reader. The technology that you use is going to make inferences based on what's supposed to happen with the data. And sometimes it just doesn't know how to handle it at all. Sometimes it'll just blow up. In the case of the example that I just showed, I would fully expect an error to be raised within whatever programming language I'm using. The 2D dimensionality of CSVs is sort of implied based on what I mentioned before about the dictionaries. Once we get into nested dictionaries or nested data types within values for a CSV, it becomes really, really challenging to handle this consistently, mostly because programming languages and the notation of how nested data are treated vary from language to language and library to library. And then I think I covered the row-wise orientation, so that might be a duplicate here. CSVs are sometimes used because they were the best option available at the time. I don't raise any of these issues to fault anybody for using CSVs. They're completely interoperable. They're really simple. Pretty much every technology on the planet has a way to read CSVs, so they're really great in that way. But something that's worth noting here is that they're also used because they're really easy to see, and as a result, trust. I think we have a tendency to trust things that we can see really readily, and that's one reason I think that they end up being relied upon pretty frequently. So large data handling often involve working with data values that we cannot see. So even if we have CSVs, we might have so many CSVs, or we might have such a large CSV that we cannot scan through it within a reasonable capacity. And I mean that both in terms of values as well as the number of columns. So and this especially kind of leans upon the big data V's, volume, variety, and velocity. So there might be so much data that we can't take a look at it. There might be so much variety that our human eyes can't really understand what's going on inside of that data. And then there might be such a rate of change on that same data that we're not able to detect using our eyes what's even happening reliably. So oftentimes we kind of think, I kind of think of this as we're up against this data deluge. There's this crazy amount of data that we have available to us, not just in bioinformatics, but across the world. There's more and more data being created all the time, and the type of that data and the variety and the velocity of that data is ever increasing, seemingly. So maybe to combat this, some things have to be believed to be seen, and this is a quote from Madeline Millionville from A Wrinkle in Time. So believe with me for a moment on the promise of Parquet, or perhaps other data formats on data that we cannot directly see. I think there's a lot of freedom in letting go of data that we have to directly witness in order to do something valuable with it. But besides believing, because a lot of us are, I think, objective and pragmatist and into science, there's a lot of measured performance benefits to using formats like Parquet. I'm not going to belabor these because, quite frankly, these articles do a better job than I can in terms of spelling this out, but usually it's orders of magnitude, anywhere from like 30 times to 100 times faster to use something like Parquet compared to CSV. And I have some links down here, which I'll share again with the slides after today's presentation, one from Posit and another from dzone, but there's these are sprinkled throughout the web. You don't have to look very far to find examples of this. So enter Parquet. So Parquet defines itself as a columnar data storage format available to any project in the Hadoop ecosystem, regardless of choice of data processing framework, data model, or programming language. Hadoop is a data processing system that was popularized by, I think, originally Facebook, who deals with gobs and gobs, I think some of the largest amounts of data in the world. And regardless of what you think about social media systems, in terms of Facebook or Twitter or any of the companies that were involved in creating Parquet, it's worth mentioning that they deal with massive amounts of data that we can benefit in terms of from their findings of technology developments. Some rough history. Parquet was inspired by earlier work from Google Research in 2010, a paper called Dremel, Interactive Analysis of Web Scale Data Sets. And this is specifically where I believe Parquet gets the columnar orientation. It's not a direct correlation, but it's inspired by that paper. The actual technology of Parquet was introduced by collaborations between Twitter and Cloudera in July of 2013. Suffice to say, Parquet's been around for a little while. It's not exactly new. Parquet also joined the Apache Software Foundation in 2015 as a top-level project. So it's completely open source. It has its own governance procedures. And it's not like you have to rely on Twitter or Cloudera or anybody else who adds contributions to the project in order to take benefit from it. So maybe contrasting with that CSV file that we were looking at, this is what a Parquet file will look like if you try and open it up or look at it. It's really just going to be this file. So again, we kind of lose that ability to see the data anymore, which can feel like kind of a pitfall when dealing with sort of transition from data that we can see to data that we can't really see. So what do we mean by columnar data? So in that description, Parquet describes itself as a columnar storage format. So if we wanted to contrast the columnar part of Parquet with something like CSV, take for instance that we have this CSV file and two columns, one column that has numbers and another column that has fruit names in it. So in terms of how that data is organized on the file, we get read back one and then grapes, or one and then grapes in terms of the row, and then two and then oranges, using the new line as the way to delineate those values. Whereas Parquet, on the other hand, is more organized something like 1 and then 2, where all the values of the columns are organized together. And this directly correlates to some of the performance benefits that you can see from Parquet. Something that's interesting, and I don't go over later in this presentation, is that you can read singular columns from Parquet without having to incur a full read of the data set. This becomes really important when you're dealing with super large data sets where you only maybe need a couple of columns out of the data. You don't want the whole thing. You don't want to spend time just waiting for something to be read that you're not going to use.
I have a quick question, if that's okay. So does the performance of Parquet sort of scale in relation to other readers or formats when you have particularly long data?
I think it's going to depend. Parquet does some magic in terms of encoding based on the type of data that it receives. So if it has a bunch of repeated data, so like repeated values, it'll use certain encodings, and it'll do this on a per column basis to make sure that you get the best performance possible. And usually that encoding is being balanced with compression at the same time. So there might be compression, there might be no compression, depending on what options you select as far as the data write and read times.
Okay, thank you.
Yep. So jumping a little bit further into the internals, so Parquet organizes column values into pages instead of row groups. Row groups are sort of up to us sometimes as far as what we want to do to organize the data. And again, towards the point of some of the automatic selection of encodings. Some of this takes place under the hood, and we don't get too much option, but generally there's usually a way that we can customize the data. The default settings are usually sufficient to decide on what is best for the data, but not always necessarily. Row groups contain basically chunks of columns that are organized as pages, and the pages are the core of where the encoding and compression takes place. These are in addition to separate chunks of the data that deal with the schema and the metadata of the file. So that's handled separately. So you might be thinking, okay, already show me why any of this matters. It's fairly technical stuff, so I apologize, but mostly just trying to equip you with an idea of how and why Parquet operates the way that it does. So in other words, how can we use this today? So we kind of covered this earlier, but have you ever experienced mixed data types in your data? These are really challenging and really expensive to resolve. Once these are in place, we usually can't fix them, oftentimes because we're relying on data that's already been published. And making translations of that data is sort of our own inference of that data. We're basically deciding to correct data that's already been put into place. Even for our own data, it might be difficult to figure out exactly why something happens. And we're usually moving as fast as we possibly can to correct things as we go, let alone resolve historical data issues. So Parquet has this notion of strongly typed data. So I'm grabbing this term from software development, but essentially Parquet doesn't let you store data of different types or data values of different types once you have a certain type that's associated with the column. So in the example here, so this is using Pyro as a way to interface with Parquet. I have a Python dictionary here that shows columns A with an integer, column B with strings, and one different value, an integer mixed with strings, and then column C with floating point values. When we go to try and create or write this table, there's an error that we get. It's an arrow type exception, which I believe comes from arrow specifically, but even if you try and do this in Parquet, it will raise an error because you're trying to shove a data type value that doesn't align with the column or the rest of the column values. So this becomes really important to avoiding those challenges that I just mentioned as far as performance and also expectations. And it basically shifts us left on the testing spectrum, that we didn't even have to write a specific test to make sure that this thing didn't happen. It automatically prevented it from happening right away. Another thing that Parquet can do is it has complex data handling capabilities. Parquet files may store many data types that are complicated or impossible to store in other formats. And this is sort of something that I mentioned about the CSV not being able to consistently store the dictionary that I showed earlier. So things like numbers and strings get stored just fine within Parquet files, but we can also do things like store images or byte arrays or lists, things of that nature. And so this is a quick example using PyArrow to demonstrate that we can store nested values, things like a struct or a dictionary, where we have values within values, and these just lists of lists, basically, or things like a byte array. So this is just taking an emoji and encoding it to a byte array, and then trying to store that as a value inside of Parquet. And there's nothing else that's really necessary here. We just take the table and we put it into Parquet, and then we read back out the schema from that, and we can see that we have the data types that are strictly cast, and so we know what we're getting whenever we try and read data back out of that file. Parquet
So does it mean when we call these particular elements from within Parquet, we can perform the corresponding operations? For example, if it's an image, or I don't know if it also takes in plot objects, right? For instance, for different subsets of data, maybe you're creating these plot objects. So then whatever we can do with the plot object, or whatever we can do with key value pairs. So does it mean when we call upon that element, then we can perform those corresponding operations fairly easily?
Yep. Yeah, it's going to depend on the language and the library that you use to read it back out. But typically, yeah, it's a matter of accessing that element and then performing whatever tasks you might have to work with. Parquet also sort of embeds the notion of compression almost by default in terms of the libraries that interface with it. Usually, when we have a Parquet file, it can be understood to be compressed, not always, but pretty nearly always. And this is in part due to the fact that it reduces the size of the data that you're going to be working with, and it also increases the read times, or decreases the read times in terms of reading that data back out, because all the data that you're reading out is smaller. Usually that compression that's used with Parquet is an algorithm that's called Snappy, but it has flexibility to use things like Z-standard, gzip, and any number of other compression technologies, depending on what might work best. The type of compression that's going to work best is going to be contingent on the type of data that's used, and also the technologies that need to be used to read it back out, or read the data back out from the file. Parquet treats metadata as a first-class object. So the way that I usually think of this in my head is we have a Parquet file, and on the one hand, we have the column data that's treated in a particular way, but then we also have the metadata that's associated with that, that data. This is distinct from other libraries. In specific, I can think of pandas, which doesn't make your schema necessarily a separate object. You infer that information from the column data itself, which can be quite difficult to work with, especially when you only want to know about the metadata. Like, let's say that the data is so large that you don't want to read any of the data at all. You just want to know what the data is about and what columns are in there. And for instance, how many rows or how many columns there are within the data. You can grab that information without having to touch the data values at all within Parquet. This is a quick demonstration of customizing that data. So in addition to knowing just basic information like the column names and maybe row length, things like that, We can also replace the schema metadata, so we can add our own custom information to the file, which is really, really crucial as far as describing, especially where the data came from. In this case, I'm in this code, I'm adding schema metadata that just creates a key called data producer. And then I just called this CUDBMI set for the software engineering team. So this means that this data, when we write it to this file, will have that information associated with it by default. We don't have to include another metadata file. We don't have to rely on somebody mentioning in a markdown file where the data came from and how to provide credit or attribution. They immediately know just by having the file where it came from, so long as they read that metadata. And in terms of how this looks within the file, once we write it, you can read back out the schema, and it'll print out not only the column names and their types as well, but also the schema metadata that can be associated with that file. And really anything you can imagine could be put in here. It takes a string value as an input from Pyaro, and I'm pretty sure that that persists down to the Parquet requirements. So pretty much anything imaginable, including additional code or perhaps JSON schema or other details that you might want to include along with the data. Parquet includes capabilities for multi-file data sets. So Parquet files may be used individually or treated as a data set through file groups, which include the same schema, column names and types. So here I just have a simple file tree showing this Parquet datasets directory, and then we have dataset 0, which might have one or many parts. All of these files will have matching column names and column types. And then you can simply pass this directory in terms of reading that data. And then the same thing for, say, another data set that you might want to work with. And you can slice this up however many times you want, so all the way down to individual columns if you wanted to recompose the data however you might see fit. This might seem like a nuanced case, but it becomes really important when you're dealing with having to download, say, multiple files, or dealing with systems that have file size constraints that might be really inhibiting as far as your ability to get work done. There's also inodes to consider. There are file size limitations that you eventually reach that the file system has, and this deals with the concept of inodes, and it's basically a system limitation that you can't get around. So being able to split up the data set into these multiple chunks can make a whole lot of sense depending on the data that you're working with. So this is a quick example in terms of doing this from Python. So let's say that we have two tables that we're creating that have one column with one value in the first table and then two values in the next. So these both have the same columns. They're both going to be of the same type. It's just numbers. It's the column A. So if we wrote this to two files, so we have dataset example1.parquet, dataset example2.parquet, we'd then be able to read that as a Parquet dataset using just the directory. And then this .read here does all the work of reading the data in. We don't actually have to read the data. We can be quote unquote lazy about the operations here. Which again come with their own performance benefits. If you have, say, millions of files that are of all the same schema, you can do some other work here to make the software a little bit more efficient. And in terms of how this looks, by default, you'll end up with row groups that are split based on the way that the data was read from that data set. And again, you can customize this a bit depending on what might make most sense for the data. All I'm trying to say here is that this might look a little bit weird with the lists within a list here, but it's really going to be treated as one cohesive column with different row groups there. Parquet also has really robust integration with the Apache Arrow project, which enables cross-lingual interchange to take place. Basically, we have a Parquet file, and then we might want to read that same Parquet file using, say, R, Python, or Julia, or any number of other languages. But perhaps the default readers in those languages all think about the in-memory form, the in-memory representation of that file-based data differently, which is really troublesome when you start to try and troubleshoot some of these issues. It can be caused for a number of different time-consuming issues, like how nulls are treated, how say floating point are treated. But the Arrow project provides us a consistent way to read the Parquet data in all the same way, essentially, because it unifies the way that data is represented in memory across these languages. This is a quick attempt to try and define this, and probably not the best example, but I did my best here to show the schema of both this Arrow table here, as well as the schema from the Parquet table, and recognize the limitations here of using PyArrow for both. So I haven't done the best job of demonstrating this, but we're printing the table, like the in-memory table schema types, as well as the Parquet files schema directly reading from the file that was written above, and we get back the same data types, which is, again, really important to being able to handle the data in a consistent way. So this cross-lingual implementation means that we have more people able to participate in the same data conversations. It really just opens up the doors to possibilities, and I think really steps aside from some of the, say, sometimes pointless arguments between which language has a better interpretation of a certain data, certain chunk of data, or certain data file format. It also decouples us from the limitations of just one language. If we're locked in to one language, that reduces the capacities for innovation. So it might be that certain languages have benefits in terms of performance, or say statistics, or whatever we might be trying to accomplish. And so we can use whatever language might suit us best. I think in research, we're accustomed to the notion of notebooks and maybe cross-lingual implementations, that there will be multiple languages that are used to help compose a project, most notably through, say, R-based notebooks, Jupyter notebooks, Quarto, you name it. I think it's also worth mentioning that Parquet helps us to enable fair data practices, and that is findable, accessible, interoperable, and reusable. So the data become findable because we can publish these data sets, and they're readily queryable in terms of open data sets. We can make them smaller via those chunks that I mentioned in the data set options that I mentioned. They're accessible in terms of being able to read back the data in a consistent way. They're interoperable in that many languages can use that Parquet format, and they're reusable. You can remix Parquet data sets how you might see fit using various clients to read back that data. It's not just about one Parquet data set. You can start to intermix these things using things like the IDIS project and DuckDB to intermix various data together. So how can you use Parquet? There's a number of different libraries and ways to interface with Parquet. So Pandas has the PD dataframe.to Parquet. So if you have a data frame, you can write directly to Parquet from within Pandas. And then there's the PD read Parquet option. Read Parquet can take in individual files as well as those data sets that we were talking about before. Apache Spark ties into Parquet files, and there's a whole guide on how to interface with Parquet files from Spark. PyTorch has an object or a class called the Parquet data frame loader, which can help you to load up data from Parquet files. And then there's the PyArrow project, like a quick guide on reading and writing Apache Parquet format from the PyArrow project. R also has a number of ways to interface with Parquet through the Arrow project, which directly ties into that same Arrow project that I mentioned on the other slide with Python. There's the write Parquet and read Parquet options. And usually these Arrow is used in tandem with dplyr. And then there's also DuckDB, which provides an R API and has its own way of interfacing with Parquet files. If you liked any of this or any of this piqued your interest, yeah, I encourage you to read about the Apache Arrow project, an in-memory data format which enables high performance and unified memory handling across multiple languages. There's DuckDB, which enables SQL queries over local or remote Parquet files. And then there's also the IBIS project, which is a Pythonic API for Parquet and many other formats in terms of data handling. And that's it. So thanks for attending. I'd love to hear any questions or comments that you might have, and please don't hesitate to reach out to either us on the PDMISAT team or directly. Feel free to find me on GitHub.
Thanks, Dave. We have about 20 minutes for questions, so if anyone has any questions, online as well.
This seems really cool. So, for example, you said it works seamlessly with splitting large data sets across files. So you think that might especially be compatible with GitHub's limitations? So without using LFS or something, you can still just split it across multiple files and easily make it part of a data package in GitHub or something.
For sure, yeah, yeah. So if you're running into the like 2 GB limitation or whatever,
or 100 MB usually, but yeah.
Oh wow, yeah.
With LFS, it's slightly larger, but otherwise it's really pretty small.
Yeah, so if you're running into the 100 megabyte limitation, Parquet, those compression options are really great depending on the data sets that you're working with, and you can use that to split out into those directory structures like I mentioned. I'm not sure offhand what the file count limitation might be for a GitHub repo, but that might be something else to consider.
Okay, any other questions? Also, as a part of the seminar series, we are trying to ask speakers to stay a little longer to talk with any trainees who want to talk in an informal way. So if you could stay a couple minutes just to see if anyone's. Great. All right, thank you, everyone.
Yeah. And I especially want to thank Dave for stepping up at a really